All right, so welcome everybody to the Flow seminar, where Flow stands for Federated Learning One Word Seminar. For those of you attending for the first time, this seminar was designed to provide a global online forum for the dissemination of latest scientific research in all aspects of federated learning. That might include distributed optimization, learning algorithms, privacy, cryptography, and many more. So a few technicalities before we start. This talk is recorded. If you want to ask questions, we have all mics disabled by default. So if you have any questions for the speaker, then either just raise your hand. That's option is available in the participants menu, or just post your question to the chat. And what I'm going to do after, I'll try to unmute you so you can actually ask your question in person and have a bit of an interaction with Krishna. So for today's talk, it's my great pleasure to introduce you our speaker, Krishna Pillutla, who is currently a visiting researcher postdoc at Google Research working in the Federated Learning team. He's working mainly in machine learning, artificial intelligence, optimization, and robustness. Prior to joining Google, he completed his PhD in the University of Washington, and also his research was recognized by many awards, for instance, NEVREP's Outstanding Paper Award, and also he was JP Morgan PhD Fellow. So Krishna, it's a great pleasure to have you here, and please, floor is yours.
Thank you. Thank you for the kind introduction, Samuel, and thank you for inviting me. I'm delighted to be able to present this talk. So today I'm going to talk about federated learning with partial model personalization. This is joint work with collaborators from Meta AI, Kshitij, Abdo, Mike, Maziar, and Lynn. And this work has been published in ICML this year. So machine learning models are everywhere. They're in our pockets, on our phones, making predictions as we type and interpreting our voice commands, and a whole lot of other apps. They're ubiquitous in the healthcare setting, helping doctors diagnose their patients and provide care. And now increasingly, they're present on our roads with the advent of self-driving cars. The common theme across all of these examples is that the data that is used to train these models is generated in a decentralized manner and is moreover private. Think about our healthcare records. We certainly don't want anybody else seeing them. The dominant machine learning paradigm in this setting today is federated learning, as you very well know. It was introduced in 2016 by researchers at Google, just as smartphone ownership was exploding. And it was introduced as a way of training machine learning models on smartphones, but now it's used more broadly across all of these examples that I described earlier. So for the purpose of this talk, we are going to define federated learning as a learning paradigm where the data that is used to train the model is decentralized on a number of client devices. The training takes place on these devices with no data being transferred to a server, but there is a server that coordinates the training process. Now, for a first order approximation, it's reasonable to assume that the communication cost dominates the computation cost, because in smartphones and other edge devices, the bandwidth is constrained. While federated learning has had many successes over the recent years and is now deployed on a global scale, it also faces some challenges. And the challenge that is relevant to the talk today is that the models are deployed on clients with heterogeneous data. In the cross-device setting, each client corresponds to one user, and the data generated by that user has the characteristics, has their unique characteristics. And therefore, one trained model globally is now deployed on individual users whose data distribution is different from the population average. Now, this has several ramifications in practice. One important one is this so-called accent gap in smart speakers, where research has found time and again that the model does worse than average on minority groups. For instance, both Google Home and Amazon Echo have pretty high overall accuracy, upwards of 80%. But on Spanish accents, the identification accuracy is about 3 to 4 percentage points smaller, which is a significant drop. So one approach that has a natural approach to tackle this problem, and one that's used widely and even deployed in practice, is model personalization, where we adapt the model individually to each client, or just a part of the model. Now, this is a manifestation of the usual pre-train, fine-tune paradigm of transfer learning. And as I said, it is widely used in deployment. So for the purpose of today's talk, we are interested in partial personalization, where only a part of the model is personalized. The rest of the model is shared across all of the clients, and some layers are specific to each client. This idea has also been explored very broadly and widely in the literature. For instance, starting in 2019, Arivasagan et al. Proposed to personalize the output layer of the model so that each client can train their own predictor atop a shared representation. And then they suggest training both the personal and shared parameters simultaneously in an algorithm that looks very much like federated averaging. On the other hand, in 2020, Liang et al. Suggested, let's instead personalize the input layer of the model so that the input layer that processes the privacy sensitive inputs remains on the client. And then the rest of the processing can be shared across the clients. This makes sense. Just like personalizing the output layer was motivated by the vast literature on multitask learning, personalizing the input layer is similarly motivated by the literature on domain adaptation and covariate shifts. So again, they suggest training both the personal and shared parameters simultaneously in an algorithm that looks like federated averaging. So it's identical to the algorithm proposed by Arivasagan et al. And then 1 year later in ICML 2021, Collins et al. Said, no, let's go back and let's personalize the output layer again. So similar to the first one. But instead, let's train the personal and shared parameters in an alternating fashion. So their modeling approach was similar to the first one, where again, there's a shared representation and a personal prediction atop the shared representation, but the optimization is different. And then later last year in Europe's, Singhal et al. Said, yeah, this alternating optimization suggested by Collins et al. Is a good idea because the personal parameters can now be trained from scratch each time. So you don't have to keep them around. Like each time you start from scratch, you train up the personal parameters, bring them up to speed, and then train the shared parameters. So looking at all these prior works, we're faced with the question, how, given a new application, how do I choose in what way to personalize the model? In particular, what modeling decisions to make? In other words, what part of the model to personalize? Should I personalize the input layer, the output layer, something in between, something else, maybe a combination of the two, is not clear at all. And secondly, what optimization algorithm do we use? Do we use the alternating update one, the simultaneous update one? And there is limited theory for the alternating update algorithm. So in this backdrop, our contributions are twofold. First, we analyze the theory of both of these optimization algorithms in the general smooth and non-convex case. And second, we provide extensive experiments in various AI domains like text, vision, and speech. So The modeling question is handled in the experiments, where we find that the type of personalization should depend on the type of data heterogeneity in the task. So the choice of personalization, or the modeling choice and partial personalization, should come from a knowledge of what the data and task are like, and we shouldn't stick to one method across all of the tasks. Second, when it comes to the optimization algorithms, our theory suggests that the algorithms have the same asymptotic rate, but the alternating update algorithm has a slightly better constant in typical practical settings, and the experiments corroborate that. Okay, so with this introduction in place, let's move on and to talk about first setting up the problem formally and reviewing the different algorithms. In the second part of the talk, we'll look at the convergence analysis of these two optimization algorithms, what goes into that. And finally, in the last part, we'll turn to the experiments across these different AI domains. So let's start with the first part, with the setup and review. It's helpful to recall the usual non-personalized federated learning setup first. Let's suppose we have n clients, numbered 1 to n, and whose data distributions are denoted by P1 to Pn respectively. Because of the data heterogeneity, each of these distributions can be different. And the learning objective in this case is to minimize the average loss across all of the clients, where the loss on one client measures how well the model fits the data on that particular client. Notice that in the usual non-personalized setting, there is just a single model across all of the clients. Now, in the personalized case, with partial personalization, we're now going to split the single model W into two parts. Parameters U that are shared across all of the clients, and parameters VI that are personal to each client I. Putting these two, concatenating these two together gives the full model on one client. And then the objective, similar to previously, is to minimize the average loss across all of the clients. But now the average loss is a function of both the shared parameters and all of the personal parameters. So our objective will be to minimize all of these parameters at the same time. Now this setup is fairly general. The two examples we discussed earlier of personalized input and output layers are of course a special case of this, because just some of the layers are shared and the others are personalized. But this framework is more general. It encompasses also the federated residual learning approach of Agarwal et al., where there is a shared model and a personal model, and the final predictions are an ensembling of both of these individual predictions. So for classification, we might want to take, say, like a vote, or maybe a linear combination of both of the predictions. We can also do something which is more sophisticated and in line with the deep learning architecture in question. For example, in a shared transformer model across all of the clients, we can have adapter modules that are personalized to each client. So adapter modules are small parameter efficient modules that change the predictions of the model by a small amount in order to personalize them. But this this framework that we consider is more general than partial personalization. In fact, it also encompasses other forms of personalization, as shown by Hanzali et al. For instance, the PFED-ME framework, which is personalized federated learning with Moreau envelopes, minimizes the Moreau envelope of each client, and it can be written as shown on the screen. So the individual, the per client objective is now a function of the predictions of the client and also the regularization term. Okay, but we'll still be focused on the partial personalization part in this talk. So let's quickly review the two algorithms that we discussed earlier, the alternating update and the simultaneous update one. We're going to give them names here. We'll call them FedAlt and FedSim, just for convenience. And the two algorithms have, as I mentioned, been used in previous work. And they're designed to be as similar to the federated averaging approach in the non-personalized setting. So in both these settings, so all three algorithms proceed in synchronized communication rounds. And in each round, there are 3 steps. So the first step is same across both of these settings, which is that the server samples a number of clients, M clients, and broadcasts the current global model to each of them. In the second step, each client performs some local SGD steps on their local data. In the non-personalized setting, it is clear what this means. In the personalized setting, however, there can be 2 choices, the alternating update and the simultaneous update. So in the alternating update algorithm, what happens is that the server shares the shared parameters U, and the client first updates its personal parameters, bringing them back up to speed in a number of local SGD steps, and then updates the shared parameters, keeping the personal parameters fixed at their newest value. On the other hand, in the simultaneous update algorithm, both the shared and personal parameters are updated simultaneously. So the server sends the shared parameters, the client appends its personal parameters, and then a number of SGD steps are run with the entire model. And then the shared part is sent out for aggregation. And the third step, of course, is the aggregation.
So Krishna, yes, please. So about the FedAlt, I wanted to ask, so if you run multiple local steps, do you alternate like first and second, or you run first, let's say, case step, and then the second case steps, or how that works?
It's the latter. So we first run a number of local update steps on the personal parameters, and then run a number of local update steps on the shared parameters.
Thank you.
Yeah, good question. Yeah, for now, it's sufficient to think that there's a single step, because multiple steps often play the role of a single big step, at least in theory. Okay, so in the third step, there's simply the aggregation. In the non-personalized part, the entire model is aggregated. In the personalized part, of course, only the shared part of the model is aggregated. It doesn't make sense to aggregate the personal parts, which could in fact have different architectures as well. So the personal part remains on the client. Okay, so those are the algorithms that we're going to consider, and let's move on now to the convergence results. We're going to analyze convergence under typical assumptions. So the first assumption is of smoothness. Now, in the usual non-personalized setting, the assumption would be that the gradient, the loss is smooth. In other words, the gradient of the loss is Lipschitz with respect to the parameters. But now we have two sets of parameters, right? The shared and the personal ones. So we're going to assume the Lipschitzness of the gradient, but now with respect to both of the parameters. So we're going to assume that the gradient of the objective with respect to U is LU Lipschitz with respect to U, and LUV Lipschitz with respect to VI. So that's the second one, is the cross dependence. And likewise, we're going to make gradient of V. It's LV Lipschitz with respect to V, and LUV Lipschitz with respect to U. So if if the objective is, say, twice differentiable, then we can take both of the cross Lipschitz constants to be the same. That can be done without loss of generality. So the key quantity here is the cross for the cross dependence is this ratio that I denote as chi squared. So that's the ratio of the cross Lipschitz constant squared divided by the individual Lipschitz constants. So if chi squared is bigger than 1, it means that a small change in u leads to a larger change in the gradient of v rather than the gradient of u. So that means the cross dependence is large. And on the other hand, if it's smaller than 1, it means that the cross dependence is small. So the gradient, a change in u leads to a bigger change in the gradient of u rather than the gradient of v. Okay. And then the bounds will of course depend on this cross dependence parameter. In the second assumption we make is the bounded variance assumption. Now, typically for stochastic gradient analysis, we assume that in the smooth case, we assume that the stochastic gradients are bounded in variance. In this case, we have two sources of variance. We have the variance of the stochastic gradients within a client and also the variance across clients. So for the first one, it's just a standard bounded variance assumption. The stochastic gradients of u and v have bounded variance sigma u squared and sigma v squared. But then for the across client part, we can view sampling a client as giving a stochastic estimate of the gradient of the overall objective. And a bounded variance assumption in this case is known in the literature as bounded gradient diversity. And in our case, with personalization, we only need that assumption for the shared part of the parameters because the personal parts don't interact with each other directly. So we have this variance only on the shared parts. So these are the three different sources of the variance. With this in mind, we are ready to state the convergence result of FedAlt and FedSim. So let's break this down. Let's start with the left-hand side. The left-hand side for both of these consists of two terms. The first term is the square norm of the gradient of the objective with respect to the shared parameters u. And the second term is the gradient of the objective with respect to the personal parameters. Now, because this is the general non-convex case, we look for stationarity condition. So we want the gradient norms to go to 0. Now, if this left-hand side converges if the right-hand side goes to 0, it means that the gradient norm of each of these parameters is converging to 0 as well. And that's the notion of stationarity we are going to go after. So for this left-hand side, the rates that we show are the typical 1/√t rates in smooth non-convex optimization. And there are a bunch of lower order terms after that. So looking at this leading order term, the difference between FedAlt and FedSim is that their constants are not the same. So these sigma 1 squared and sigma 2 squared are linear combinations of the three sources of variance: the within client stochastic gradients and the across clients diversity. So how do these two constants compare with each other? Well, the constant for FedAlt is better than the constant for FedSim when this particular condition holds. So as expected, it's a condition on the relative magnitudes of the three sources of variance. And on the left side, we have sigma v squared. On the right side, we have sigma u squared and delta squared. Delta is the across client variance. So what we see is that this condition holds when the inter-client variance delta squared is much larger than the within client variance. And that can usually happen in cross-device federated learning, where there is not a lot of data on each client. So locally, it's as if we are using the full batch gradient on each step. But there is, because of heterogeneity, because of data heterogeneity, there is inter-client variance. And when this condition holds, we find that the constant for FedAlt is better than the constant for FedSim by a factor of square root of 1 plus chi squared. And recall that chi squared, this constant, characterizes the cross dependency between both of the shared and the personal parameters. So what this says is that in typical cross-device settings, the alternating update algorithm fedalt might have a better dependence on the cross dependence than the simultaneous update algorithm. There are some technical difficulties that come up when showing the alternating update proof. Previously in the literature, the alternating update algorithm was only analyzed by Collins et al. In the simple two-layer linear network case. So there was one, it's basically the matrix factorization setting, where if you fix one parameter, the other, the rest of the problem, the partial minimization is convex. So in the non-convex case, however, typical stochastic gradient proofs proceed by applying smoothness. So to illustrate the main technical difficulties, let's assume that the within client variance, sigma u squared and sigma v squared are 0, and we are only taking a single local gradient step. So the smoothness bound for the shared parameters, assuming that the step for the personal parameters is completed, can be written as follows. So the left-hand side is just the difference, and it comes from changing only this expression comes from changing the shared parameters. So what we observe in the first order term on the right side is that both the updated personal parameters Vt plus 1 and the updated shared parameters Ut plus 1 depend on the sampling of the clients. Now for stochastic gradient proofs, the first order term has to be unbiased. So in expectation, it should be as if we're moving in the direction of the full gradient. In this case, we cannot assert that we cannot pass the expectation over the client sampling through the inner product, because both sides of the inner product depend on this sampling. In other words, we lose the unbiasedness that's absolutely necessary for stochastic gradient algorithms in this case. Just to note, for the simultaneous update algorithm, there is no such a difficulty, because in the inner product term, there is only one dependence on the sampling of clients, because the U update starts from both UT and VT being the previous state. They don't depend on the sampling of the clients, and so the expectation can pass into the inner product. So this proof can go through with minor modifications to standard techniques. Going back to the alternating update algorithm, however, that's not the case. The update is biased. So to overcome this, we use what we call virtual full participation. This is a technique that we devised in order to decouple the dependence of both sides of the inner product on the sampling. So what we do in particular is to assume that all of the clients, both the ones that are sampled and not sampled, have participated in the personal parameter update, the V step. So denote this update by Vt plus 1 tilde. And we pretend as if instead of using Vt, we use Vt plus 1 tilde. And now because this Vt plus 1 tilde has personal parameters updated for all the clients, it does not depend on the sampling of the clients used in this particular round. So what we are essentially doing is we are cutting this dependence of one of the sides of the inner product on the sampling. And by doing this, we can pass the expectation into the inner product, because now there is only one dependence on the sampling, and we can use linearity of the inner product. However, this gives us an error term, because we really should have had f of ut and vt plus 1 in the inner product, and instead we are using vt plus 1 tilde, and that's accounted for in this error term. So the crux of our proof relies on bounding this error term as something small. So in particular, it reduces as a square of the learning rate. And so by making the learning rate small, we can bound this bias just as we would the stochastic noise. In other words, this gives us a way to complete the proof in the alternating update setting. So to quickly recall this last part, we overcome dependent random variables by looking at what would have happened had we run more updates than we actually did. And then by showing that, yeah, what actually happens is not very different from that idealized setting. And for more details, I'd be happy to talk about it offline, or the proofs in the paper, of course. That brings me to the end of the section on the convergence analysis. And now we move on to the final part about the experiments. So we run experiments in 3 AI domains, as I said, text, speech, and vision. And we look at applications that might be motivated by cross-device federated learning. So the first application in the text domain is next word prediction, which is of course motivated by mobile keyboards. And speech recognition, of course, is motivated by voice commands on our phone. So the assistants like the various mobile assistants or smart devices would find applications for speech recognition. The third comes from vision, landmark detection, where the dataset consists of photos of various landmarks around the world taken by individuals and contributed to Wikipedia. So this is reminiscent of the camera app on our phone, where each person only sees a small number of landmarks, and very few people see more than a handful of landmarks around the world. So we use fairly state-of-the-art or close to models. So for the next word prediction, we use a 4-layer transformer model, which has 6 million parameters. For speech recognition, we use a 6-layer transformer model with a convolutional subsampling at the start, and that has 15 million parameters. For vision, we use a ResNet 18 model, which has 12 million parameters. The data sets are for next word prediction, we use Stack Overflow. That's a standard benchmark data set for federated learning. For speech, we use the Libri speech data set, which is a data set of audiobooks where each client corresponds to one particular narrator. And the data is, the task is speech to text. So given an audio clip of the narrator reading a part of the book, the goal is to identify what the narrator said. And the data set, of course, contains snippets from various books. And of course, in vision, it's the landmark detection data set called GLDV2. And in each of these settings, we consider a set of 1,000 clients. I'll also mention that for speech recognition, computing the loss is not so straightforward. It uses dynamic programming because the output space is the space of all text sequences and is non-trivial. So it's a structured prediction task. And in the landmark detection setting, as I said, there are a total of 2,000 classes in the data set, but each client only contains an average of 30 because nobody sees all the landmarks in the world. Like most people only see a few. Okay, so the first question is for modeling. Which form of personalization is better? Do we personalize the input layer or output layer or something in between? Well, what we find is for next word prediction, personalizing the output layer has the smallest error. And for different tasks, the best performing one is different. So for next word prediction, personalizing the output layer makes sense because most of the heterogeneity in the data comes in the prediction of the output, where different users might respond differently to the same context. So it makes sense that output layer personalization works the best. On speech data, on the other hand, input layer personalization works the best. And it makes sense here because most of the diversity in the speech data comes from the accents, where different narrators in this audiobook data set have different accents and different voices, for instance, male or female, talk at different speeds. whereas the text in this setting is just plain literary English. So most of the diversity is in the input, and the input layer personalization has the smallest error. In this case, by the way, the error is the word error rate, which is again computed by dynamic programming. Finally, in the last case for landmark detection, we find that adapter modules have the smallest error. What we find in this case is that because there are very few labels on each client, just 30 on average out of 2000, personalizing a model to a client results in catastrophic forgetting of all of the other classes. So the model basically gets the predictions of classes that weren't in the training data set wrong after personalization. Adapter modules in the context of vision were proposed as a way of preventing this catastrophic forgetting. And they, in fact, come from the literature on continual learning. So they're able to better combat the catastrophic forgetting. And we see that this leads to a huge improvement in performance. The accuracy goes from around 46%, sorry, the error goes from 46% down to about 35%. So it's an 11 percentage point improvement in accuracy. So the takeaway from all of these experiments is that we need to decide what form of personalization to use based on the task at hand. This next plot compares full personalization with partial personalization. And by here by full personalization, I mean just fine-tune the entire model locally. All of the other full personalization methods, pfedme, ditto, and the others have very similar performance. So what we observe is, so this plot shows on the x-axis the number of personalized parameters, and on the y-axis the change in average accuracy over the non-personalized baseline. And the x-axis is in log scale. So what we observe here is that we can get most of the benefits of personalization just by using personalizing a fraction of the parameters. So in the text setting, simply 1% of personalizing 1% of the parameters in adapter modules leads to about over 2/3 of all the improvement that we can get from personalization. And so 10% of parameters gives most of the 80% of the improvements from personalization. Likewise, in the vision setting, we saw that adapter modules work best. And in fact, they work better than full personalization while using only around 10% of the model parameters. So
can I have a question for the previous? This one, so here is the baseline trained like in a centralized fashion on all the data, or using Fed average? This the zero, what I believe, like corresponds to zero. Yeah.
The green dotted line is trained with federated averaging.
Okay.
Yeah, and these are the improvements that the personalized model gives over that baseline.
Okay, thank you.
Good question. Right, so the second question is about optimization algorithms. We saw in theory that the rates are the same, but the constants can be better for the alternating update algorithm, especially if the dependence of the cross dependence of the parameters is large. In practice, what do we observe? Well, so here are the results. The alternating update algorithm is shown in blue, and the simultaneous update algorithm is in orange. And what we observe is, looking on the left for next Fed prediction, for input layer personalization, Fed sim is better, but for the other two, Fed alt is better by a small amount. So because y-axis shows the error, smaller is better. And on the right side, we observe again that the alternating update algorithm is slightly better than the simultaneous update algorithm. And all of the cases where it's better is shown by a star. This improvement is very small, but we repeated our experiments over multiple random seeds. And we found that the standard deviation of each task of each number is smaller than the gap between both the algorithms. So consistently across random seeds, fed-alt is better than fed-sim by a small margin. So our takeaway here is that, well, they're almost the same, but if you have a choice, maybe preferring fed-alt would be a good way to go. Okay, so that brings me to the end of the talk. To summarize our contributions, we looked at the theory of both of these optimization algorithms. We found that the alternating update algorithm had a slightly better rate. And in practice, we also found that it was marginally better. And to show the convergence results, we had to overcome this challenge of dependent random variables. And that technique might be broadly interesting in other distributed optimization or personalized federated learning type settings. And then we also had extensive experiments across different AI domains that give empirical insights into what type of modeling choices to make with personalization. The code for all our experiments is available online. You can scan this link, or it's also linked on my homepage. And yeah, with that, I conclude. Thank you. I'm happy to take any questions.
Thank you, Krishna, for an excellent talk. Yeah, so please, if you have any questions, just raise your hand or just pose a question to the chat. Yeah, I would start with, so I was curious about, so you presented the upper bounds for fed-alt and fed-sim, right? And you had this dependence on like the cross dependence, where larger the cross dependence, then fed-alt was better, right? Was supposed, like the upper bound was better, or vice versa. I don't remember. So was this so do you think that these results are actually tight? That maybe like for your experiments, like could either like, do you have a lower bounds, or for the experiments, could you estimate what's the cross dependence and whether that's kind of reflected in the like the difference that you see?
Yeah, that's a good question. So the lower bounds, well, in terms of lower bounds, the 1/√t rate is standard. So
yeah,
you know that can be improved. And in
yes,
terms
but
of
maybe
constant,
for like constants, yeah.
Constants, I'm not sure actually. I don't know if yeah, I don't know if these constants are tight. And I can say, however, that I'm sure the order 1/t terms that we have here can be improved. So the lower order terms are probably not tight. I don't know about the leading order terms. And in terms of measuring these in practice, we tried doing that. It was not. It was a little complicated because of the like deep architectures, right? And because of the normalization layers and so on.
Okay,
So
yeah. I guess that's the issue. Yeah.
Yeah, I think you know, in a simple simulation setup, it would be interesting to see you know, something like a linear model where the personalized and shared parts are added, or in a matrix factorization type setup where it's a product of the two. Where you know, it would be interesting to see what these cross dependencies are.
And let's see, I don't see any other question, but I would have maybe one other. So do you think that this so the framework that you introduced could be extended to actually automatically pick which part of the model it should personalize?
That's a great question. So we don't know where the heterogeneity in the data lies a priori. Like here, basically, like the insights that we have come from inspecting the data, and also, you know, like domain experts who know, say in the speech setting, that the speech side is more diverse than the text side. So you know, apart from using domain expertise. The other way to do it would be to quantify how much heterogeneity there is. And there does not exist a way to do it currently in a way that reflects, so there are ways, of course, to measure diversity from an optimization perspective, but not from a modeling perspective, right? So like just purely for a model, it's not clear, like given a new data set, it's not clear which side there's more diversity on. So that's an interesting question. And that's actually something I'm working on currently, like how to quantify the diversity.
Great, thank you. And then there is, we have a question from Manav. I tried to unmute Manav. So you should be able to unmute yourself. Yes.
Am I audible?
Yes.
Yes.
Great. I had two questions. The first one being, are there any privacy measures that you were adopting when the shared parameters are being updated there?
No, so this doesn't use any privacy at all. So there are other papers that look at the intersection between personalization and privacy. We completely ignore privacy aspects. So intuitively, the hope is that if you share fewer parameters, like you pay a smaller privacy cost. And actually a tight analysis of that would be super interesting, because in most cases, like you'd only personalize a fraction of the parameters, right? Like 1 to 10%. So that does not give a tangible, like naively, where privacy just uses the dimension of the parameters, does not really give much of a benefit. But a tighter analysis would be interesting, and it's an open problem. So for the case of the two tractable cases where it's a sum of linear models or a product, the first being linear regression and the second being matrix factorization, there are some papers that look at privacy and personalization, but an overall framework is, I think, an open problem.
Right. Thank you. And the second question I had was, suppose you're taking the landmark detection and I'm getting a new test sample X. So how are you quantifying in the sense that how much weightage should be given to a shared parameter and how much to be given to a personalized parameter when I'm getting a new test X over here?
Yeah, so here we just have one model, like it's just a single model where some of the layers are shared and the other layers are personalized. And by putting both of those together, you have a full model. Like there's just one model, and it's split, right? So some layers are personalized and some layers are shared. We don't experiment with multiple models here.
Right. Right. Thank you so much for the great talk.
Thank you.